the root z. The root z is equal to under root of a square plus b square and is defined as the distance between the complex number a plus iota b and 0. R is equal to modulus of z. The argument of z is defined as the angle made by the vector. Angle made by the vector. The vector is used to show the complex number or represent the complex number on the argand plane. Angle made by the vector with the x-axis. The angle is measured both clockwise and anti-clockwise. It varies from 0 to pi and 0 to minus pi. So the range of alpha or the argument of the complex number can be termed as minus pi to pi. Polar form of a complex number. It's very common in the case of complex number. We represent the complex number in terms of the argument. Z is equal to r times cos theta plus iota sin theta, where r is equal to modulus of z. R is equal to modulus of z, the distance between the complex number and the point 0, 0, and theta is the argument of z. Theta is the argument of z. Argument of z is equal to tan alpha is equal to b upon a. It is measured both clockwise and anti-clockwise direction. For example, convert the point 1 plus iota in the polar form. Given now z is equal to 1 plus iota. This is given in the argand form. We have to convert this into the polar form. So the value of modulus z will be equal to, compare this z with a plus iota b, will get the value of a as 1 and b as 1. The value of root z will be equal to under root of a square plus b square, that is equal to root 2, and tan theta will be equal to b upon a, that is 1 upon 1 is equal to 1, that means theta is equal to pi by 4. So we can write the z in the polar form as root 2 into cos pi by 4 plus iota times sin pi by 4. Euler's form of a complex number. E raised to power iota theta is equal to cos theta plus iota sin theta. So we can write the complex number z is equal to r cos theta plus iota sin theta in the Euler form. This is the polar form, and we can convert it into Euler form as r into e raised to power iota theta, because our e raised to power iota theta is equal to cos theta plus iota sin theta. Now let's take example. We have to represent z is equal to 1 plus cos pi by 3 plus sin pi by 3 in the Euler form. Iota sin pi by 2. Z is equal to 1 plus cos pi by 3 plus iota times sin pi by 3. Then z, 1 plus cos 2 theta is equal to 2 cos square theta. So we can write this as 2 cos square pi by 6 plus iota times sin 2 theta is written breaking down into half angles, 2 sin pi by 6 into cos pi by 6. Z is equal to, if we take 2 cos pi by 6 as common, we'll get cos pi by 6 plus iota times sin pi by 6. This is equivalent to z is equal to r times cos theta plus iota sin theta. So we know the value of r is equal to 2 cos pi by 6, that is equal to 2 into root 3 by 2 is equal to root 3, and theta is equal to pi by 6. So we can write in the Euler form as z is equal to r into e raised to power iota theta, that is equal to root 3 into e raised to power iota pi by 6. Two complex numbers z1 is equal to a1 plus iota b1 and z2 is equal to a2 plus iota b2 are equal if and only if a1 is equal to a2 and b1 is equal to b2. We can compare the real part with the real part and imaginary part with the imaginary part. So the two complex numbers are equal if both the real parts are equal and the imaginary parts are equal. Important properties of complex number. Given that if z is equal to a plus iota b, then there exists a complex conjugate a minus iota b such that z dot z bar is equal to modulus of z square. Z is equal to a plus iota b and z bar is equal to a minus iota b. If we multiply z dot z bar, we'll get a square plus b square, that is equal to modulus z square. The properties of modulus. Modulus of z1 upon z2 is equal to modulus z1 upon modulus z2. The product of z1 into z2 whole modulus is equal to modulus of z1 into modulus of z2. modulus of z raised to n is equal to modulus z raised to n. This can be proved by the fact if we consider the equation of z1 in polar form. z1 is equal to r1 into e raised to iota theta 1, z2 is equal to r2 into e raised to iota theta 2. If we consider modulus of z1 will be equal to r1 and modulus of z2 is equal to r2. z1 upon z2 will be equal to r1 upon r2 into e raised to iota theta 1 minus theta 2. Modulus of z1 upon z2 will be equal to r1 by r2. So LHS is equal to RHS, r1 upon r2. Similarly, we can prove the others. Real part of z is equal to denoted by REZ, or real part of the complex conjugate z bar, that is equal to z plus z bar upon 2. This is equal to a, because if we take z is equal to a plus iota b, then complex conjugate is a minus iota b. If we add both these, we'll get z plus z bar is equal to 2a. The value of a is z plus z bar upon 2. So real part of zn is equal to the real part of complex conjugate, that is equal to z plus z bar upon 2. Imaginary part of z is equal to z minus z bar upon 2 iota. If we subtract both these equations, we'll get z minus z bar is equal to 2 iota b, and the value of b will be equal to z minus z bar upon 2 iota. So the imaginary part of z is equal to z minus z bar upon 2 iota. Convert z is equal to r times cos theta plus iota sin theta into the eigenplane form. Given the equation in the polar form, we have to convert in the eigenplane form. R is equal to modulus z is equal to under root of a square plus b square, and z is equal to a plus iota b. Also we know that tan theta is equal to b upon a. That means sin theta is equal to b upon under root of a square plus b square, and cos theta is equal to a upon under root of a square plus b square. So the value of z will be equal to under root of a square plus b square into cos theta is a upon under root of a square plus b square plus iota times b upon root of a square plus b square. Expanding, if we solve, z is equal to a plus iota b. Taking another example, given that z1 and z2 are the two complex numbers such that modulus of z1 minus 2z2 upon 2 minus z1 z2 bar is equal to 1, and modulus of z2 is not equal to 1, then we have to find the value of modulus z1. z1 minus 2 times z2 upon 2 minus z1 z2 bar whole modulus is equal to 1. If we square both the sides, we'll get modulus of z square is equal to 1. That means modulus of z square can be written as z dot z bar. So same way we can write this as z1 minus 2 z2 upon 2 minus z1 z2 bar into z bar. Z bar will be equal to z1 bar minus 2 times z2 bar upon 2 minus z1 z2 bar whole bar will be equal to z1 bar, z2 bar, one more bar, that will be equal to z2, that is equal to 1. If we expand this, if we cross multiply, then we'll get z1 bar plus 4 times z2 bar minus 2 times z1 bar z2 minus 2 times z2 bar z1, that is equal to 4 plus z1 z2 bar dot z1 bar z2 plus or minus 2 times z1 bar z2 minus 2 times z1 z2 bar. Cancelling both these terms, we'll get z1 dot z bar, means z1 bar will be equal to modulus of z1 square plus 4 times modulus of z2 square, that is equal to 4 plus modulus z1 square into modulus z2 square. z1 dot z1 bar and z2 dot z2 bar can be written as modulus z1 square into modulus z2 square. We get modulus of z1 square plus 4 times modulus of z2 square is equal to 4 plus modulus z1 square into modulus z2 square. If we take this term this side and this term this side, we'll get modulus z1 square minus times modulus z1 square into modulus z2 square, that is equal to 4 minus 4 times modulus z2 square. Taking modulus of z1 square as common, we'll get 1 minus modulus z2 square is equal to 4 as common, 1 minus modulus z2 square, 1 minus modulus z2 square. Since given that modulus of z2 is not equal to 1, so this term can't be equal to 0, so we can cancel this term from both the sides. We get modulus of z1 square is equal to